energy technologies. Innovations in solar and wind energy, battery storage, hydrogen, fuel cells, and smart grids are making energy more efficient, reliable, and cost-effective. Additionally, digitalizations and artificial intelligence are optimizing energy management, improving grid stability, and enabling smart energy consumption. Despite progress, the energy transition faces several challenges. The intermittency of renewable energy sources, such as solar and wind, requires advancements in energy storage and grid infrastructure. Many regions still rely heavily on coal, oil, and gas, and phasing out these energy sources requires carefully planning to avoid social disruptions. Moreover, policy and regulatory frameworks must be important to support the transition. In Greece now, the use of renewable energy sources has been implemented mainly to meet household needs, such as heating, with the most widespread energy sources being the use of thermal solar system as well as the use of biomass. In addition, Greece has been a pioneer in the use of both wind turbines and photovoltaic systems for energy production. Despite this, the potential for exploiting renewable energy sources remains untapped since the development of competitive industrial production of renewable energy sources has not been achieved yet. Also in Greece, the share of renewable energy sources in the total primary energy supply has increased significantly in recent years, especially in wind and photovoltaic systems, thanks to the magnificent lift in tariffs and the reduction of technological costs. However, today, polluting conventional fuels cover the largest share of final energy consumption in Greece. Specifically, based on 2017 statistics, energy production from renewable sources reached 10.5 terawatt-hours, or approximately 20% of total electricity production. Furthermore, the largest share of electricity production from renewable sources is hydroelectric energy, although it exhibits significant fluctuations per year. In 2017, hydroelectric energy amounted to approximately 3.5 terawatt-hours. That is about approximately 45% total production in Greece. It's very small, very low. Of course, despite the disastrous environmental impacts, the utilization of lignite continues to be the main domestic fuel today. Let's now have a description of Ioannina city, which is the main city of our research point. We want to have a proposal to be this city a sustainable city by using only sustainable sources and renewable sources. As the energy transition stands as one of the greatest challenges of the 21st century, cities play a crucial role in adopting sustainable practices. Ioannina is the capital city of the largest in the Ilios prefecture, and it's close to Italy, not close to Italy, the west part of Greece, with a population of about 130,000 inhabitants. The city is built on the bank of Pamvotida Lake, as you can see here in this picture. The altitude is about 500 meters. The city of Ioannina features a diverse, rich geomorphological landscape, blending mountains, lakes, rivers, and plains, making an ideal candidate for the implementation of renewable energy sources technologies. By utilizing its geographical advantages, the city can integrate these technologies efficiently to improve energy production, reduce carbon emissions, and improve energy security. Moreover, the Ioannina region has several renewable energy sources projects, mainly in the field of wind and hydroelectric installations due to the altitude and weather conditions prevailing in the area. According to the Regulatory Authority of Energy, there are 165 licensed renewable energy resource projects in the regional unit of Ioannina, including wind farms, small hydropower plants, photovoltaic systems, and biomass processing units. Ioannina, a city rich in natural resources, has significant potential for harnessing renewable energy sources. Its geographical locations and climate conditions allow for the development of solar energy, wind energy, hydroelectric energy, and of course biomass. Let's have a look at the hydropower potential and the geothermal energy production from Lake Pamvotida for Ioannina. The region is home to several rivers, including the Aouz, River, Aracos, and Kalamas, which could be harnessed to generate electricity through small-scale hydropower plants. Lake Pamvotida offers an iconic landmark for the city, could support floating solar panels combined with the hydroelectric installations, optimizing water-based renewable energy generation. Furthermore, Lake Pamvotida offers significant potential for geothermal energy utilization. The lake's thermal properties, combined with modern renewable energy technologies, can be leveraged to produce clean and efficient energy. The stable temperature of the lake's water throughout the year makes it an excellent source for geothermal heat pump systems. These systems use submerged heat exchangers to transfer heat from the water to buildings via district heating and cooling network. Moreover, a seasonal thermal energy storage system can be developed in Lake Pamvotida, where excess heat from solar or industrial sources is stored in the lake and later retrieved for use in heated application during colder months. This system would increase energy security by balancing seasonal energy demand. mountain range, and other higher locations can generate sustainable amounts of electricity. By strategically positioning wind turbines in high altitude areas with strong and consistent wind currents, the city can benefit from continuous renewable energy production. The city has access to significant biomass resources, including agricultural waste and increased livestock farming, which can be utilized for bioenergy production. Establishing biomass power plants can provide an alternative renewable energy source while reducing organic waste. Let's have a look to solar energy integration and energy harvesting system from road infrastructure. Although it is an area with interesting long-lasting rainfall days, the region's exposure to sunlight throughout the year makes solar energy a viable solution for running energy transition. Photovoltaic parks can be strategically placed on the outskirts of the city and on public and residential buildings, utilizing available open land for clean energy generation. The city of Ioannina can leverage innovative energy harvesting systems from road construction to improve energy efficiency and support sustainable infrastructure. On roads with high traffic, piezoelectric sensors can be installed under the road surface to convert the mechanical energy or vehicle movement into electrical energy. Moreover, on the bicycle paths, sidewalks, the central square and the square in the lakeside area, as well as on public parking spaces and low traffic roads with durable surfaces, solar panels can be integrated into the road surface to generate electricity from solar radiation. The application of these technologies can make Ioannina a pioneer in the energy utilization of road infrastructure, enhancing the sustainability and the resilience of the city. And to conclude, the implementation of renewable energy sources technologies in Ioannina has demonstrated significant potential for enhancing energy efficiency, reducing carbon emissions, and promoting sustainable urban development. One of the key advantages of Ioannina's transition to less renewable energy sources is its geographical and climate conditions, the availability of solar radiation, wind corridors, hydropower sources, and biomass from agricultural activities provides a diversified energy mix that can enhance energy security and sustainability, of course. Summarizing, while challenges exist, Ioannina's transition to sustainable, technical, economic, and social factors through strategic the sustainable RES-based energy system is both feasible and beneficial. Basic technical, economic, and social factors through strategic planning and collaboration, the city can achieve energy independence, reduce its carbon footprint, and contribute to the broader United
part, so it can be applied to other locations also. So therefore, I find this kind of presentation is valuable. Any questions? Because each region has its own specific climate and also physical topography. So different types of energy sources can be handled and applied. So if you have questions,
have you done economic analysis?
No,
Not yet.
not yet.
Yeah.
No, economic analysis. I'm an architect, and my PhD student is a civil engineer, and so
You need an energy.
we make a research how to transform the city of Ioannina to a sustainable city and independent of energy.
Awesome.
Yes. Because as you know, the energy problem generally in the world is a big problem, and everyone has to take measures of to be independent from the global system. Yes. Because now we use fossil. We use lignite factors, like electric plants for producing energy because of the crisis as everywhere in the world. Yes, and we must avoid this in the future.
any other questions?
Thank you very much for the presentation. My question is, energy needed in the city is only renewable energy in the city.
In the city, yes?
Yes. It is only renewable source.
It is only asked about you have in this city only renewable energy or any other traditional energy?
Or mix.
Only for this city. Only for this city,
Wait.
yes.
Only.
This city, yes, yes.
Okay.
It means, is it 100% renewable or mixed from fossil fuel and renewable energies? 100% renewable energies. That's it you're talking about. Will use 100% of
Green energy
or a mix
Do you have
of
also
fossil fuel and
traditional
renewable energy.
In Greece,
In that city, yeah.
when we use
Yeah.
in
Ioannina.
or in Ioannina.
Yeah.
In Ioannina, there are a lot of projects in order to make this city independent of energy. We have some other paradigms in Greece, some islands are independent of energy, like Tilos Island, which is located in Dodecanissa. It's nearby to Turkey. It's independent and uses only renewable sources.
100%.
100%.
Yes.
Yes. In
Because
Ioannina,
they don't have river in the islands, so
yes,
you have
the islands in
Yeah.
Greece have a big problem
Well,
of energy. Because they are linked, connected with the main area of Greece.
Yeah.
Or some of them have their own power plants, small one, and use only petrol.
Centralized maybe, centralized. Well, self-sufficiency.
No,
green energy.
no, not just that.
Wind energy, tidal energy.
Not wind, not wind. There is a small amount of islands. But they use oil, yes, oil,
Oil-based.
oil.
Traditional.
Yes, yes, yes. But the problem, I think, in Greece is we have, I think it's political, first of all. Yes. And we produced some of it by renewable energy sources, but we don't have enough places to storage this energy. That's the problem. And of course now we use electric power plants for energy because of the crisis, and because we must keep our prices in how, yes.
So, your question?
For the need of heat, the need of heat in the island, it is not possible to use geothermal energy, for example.
Thermal, it's the only parking we have is on the lake. In the lake, that's why we research this area because it has a variety of renewable energy systems, and they are not all over Greece. It's especially in some areas. Yes, we don't have thermal energy.
Okay.
Other questions? Yes?
When you have a low condition to have a renewable source, what type of energy you can use?
We may have
Low water condition to have a
Better
renewable
condition, better condition. wind,
better condition.
What type of energy you use in this?
Climate and climate reasons.
It's the same. No, we don't have another facility or something. It's the same generally in Greece. We use about 80% lignite energy production and 20% from renewable energy sources. Something like that, yes.
Thank you.
So, any other questions? Okay, thank you very much. So, this certificate is for you.
Yes, thank you very much.
Okay, so we now, before we move, last speaker, Mama, line, it's like lemon.
It's somehow.
Okay, so he will talk to capacity factor of renewable energies accurately reflect real world performance. That's very interesting.
Yeah.
Let us.
Hello everyone. First of all,
Maybe you can also get that one.
First of all, thank you for the opportunity to speak. Today I'll talk about energy development and answer the question, do capacity factor of renewable energy accurately reflect labor performance? Let's start first with the motivation and research gap. Despite rapid growth of renewable energy capacity, specific portion is being curtailed, leading unfortunately to wasted, clean and valuable energy. Also, the conventional capacity factor calculations, I mean the current equation ignores curtailment, which underestimates the system's true generation potential. This misrepresentation affects energy planning, investment decisions, and policy development. So an improved capacity factor that includes curtailment is essential for accurate performance assessment. Research problem can capacity factor metrics compare the actual versus maximum output, but again ignore curtailment. This omission leads to underestimated performance and misrepresentation of renewable energy or the reliability of renewable energy systems. This issue is even more severe in large-scale systems where curtailment is significant. Also, existing literature lacks a differentiation between household scale and large utility for capacity factor behaviors. As a result, renewable energy curtailment or renewable energy planning policy investment decisions are based on incomplete data. So what is curtailment? Curtailment is the intentional reduction of renewable energy output even when the system is capable of generating power. Okay. This typically occurs when grid demand is low, storage is unavailable, transmission capacity is limited, overgeneration risk creates stability. So energy here again is wasted, leading to lost revenue, lower capacity factor, and more fossil fuel backups. Research aims to revise the conditional capacity factor formula by incorporating curtailed energy, to assess the real-world impact curtailment using case studies, and to propose and assess practical solutions for minimizing curtailment. Here's the methodology I used, system dynamics approach. System dynamic is a powerful approach that is used to understand complex systems. As we can see here, this is the first scenario, the base case scenario. The second scenario is low change scenario, and the third scenario is based on 5-year rolling average scenario. This model is not only calculating the curtailment but also calculating the CO2 cost emissions resulting from curtailment, like for example environmental cost, health cost, social cost, etc. Here are the findings for the case study used, which is Jordan, my country. The blue line curtailment for wind energy, as you can see. The orange line is curtailment for solar energy, and the gray line is total curtailment for both solar and wind. From 2018 to 2022. As we can see, the highest amount of curtailment was for wind in 2020. Around 40% of wind was curtailed. Significant amount of energy. The lowest is 2022 for both solar and wind. The total curtailment around 3,000 gigawatt hour. To put this into perspective, this amount of energy can supply free electricity to around 1 million homes in Jordan. Very significant amount of energy. Let's compare the traditional equation versus the revised equation I suggest. The traditional capacity factor, as you know, equal the actual energy output over the maximum possible energy output. This equation ignores curtailed energy. It's unfortunately used widely in reports and models. and it underestimates system performance when curtailment is high. Why? The equation I recommend for the first time, I suggest to use this equation where capacity factor equal actual energy output plus curtailed energy over maximum possible energy output. This equation includes curtailed energy spikes down, it reflects true system performance, and it's essential for accurate renewable energy planning, investment, and evaluation. Implications of the study: we have technical and planning implications, we have economic implications, policy implications, environmental implications. For technical and planning implications, we have revised capacity factor formula provides a more accurate assessment for renewable energy performance. It also helps identify underperformance due to grid limitations, not due to system efficiency. It enhances grid planning by highlighting curtailment hotspots and missed potential. For economic implications, additional capacity factor, the current one, underrepresents system potential, leading to misjudged return on renewable energy investment. The revised capacity factor enables better financial forecasting and risk assessment, supports pricing and incentive policies aligned with actual energy yield, not just delivered output. For environmental implications, ignoring curtailed energy mass through emissions offset potential. Accurate capacity factor supports more effective carbon accounting and net zero strategy. For policy implications, informs policy frameworks on renewable integration and grid upgrades. It also encourages the development of curtailment mitigation strategy like storage, grid to vehicle, vehicle to grid. It justifies support for new applications like reducing green hydrogen and ammonia from this waste energy from curtailment. So, solutions and strategies I recommend or I suggest: use of electric vehicles as flexible storage, electric vehicle and vehicle to grid to absorb curtailed energy and support grid balance. So here the electric vehicles owners have two solutions. First is grid to vehicle. Through this solution, the electric vehicles owner can store or absorb this energy and use it at a lower price. For the second option, vehicle to grid, the electric vehicles owners can send this energy back to the grid when demand is high. Selling it. So this option is or can be considered as a source of income for the electric vehicles owner. Demand shifting through litigations. This strategy can be used by the power company by sending the customers or consumers notifications on their mobiles telling them the availability of curtailment, so they can use it at low price. Storage and demand response are preferred over expensive grid expansion, surely, because expansion in the grid is very costly. Integration with green hydrogen ammonia production, as I said, this could be a new application to use this energy to produce hydrogen and ammonia through curtailment. But it needs to be investigated. Finally, apply revised capacity formula, the one I suggest, to better reflect the renewable energy potential and inform planning. Conclusion: to sum up, traditional capacity factor assessment calculations underrepresents the performance of renewable energy systems by ignoring curtailed energy. This study introduced a revised capacity factor formula that includes curtailed energy, providing a more realistic evaluation. Curtailment significantly affects the actual generation potential and economic visibility. of renewable energy projects. Solutions such as electric vehicle storage, electric vehicle to grid, demand shifting, green hydrogen, ammonia, production through curtailment, help mitigate curtailment. Finally, applying this revised capacity factor approach enables smart investment, improved policy design, and more accurate energy planning. Grazie, thank you.
Questions?
Got a question? Thank you for interesting talk. Really, I was not aware of the amount of the curtailed energy. It's huge. But my question is, what is the amount of flexible energy, of solar and wind energy that the grid can sustain? Because it is risky.
You mean in Jordan?
Yeah,
or in
not in any grid, let's say. Because we know, for instance, in Spain, some time ago, there was a
It
huge
depends on the country. Okay, in Jordan, there was a high amount of curtailment, as I showed in this figure with the findings. As you can see, for example, in 2020, around 40% of renewable energy generated, 40% just gone. So it's really a huge amount of energy.
Yeah.
We lose it. Okay. In other countries, some countries can reach 80%. Some countries less than this number or this percent. So it depends on the country.
But my question is, okay, you need to lose this energy because otherwise the grid risks to be unstable.
But then,
So what is
because of that, I suggested some solutions to absorb this curtailment, like the ones I said regarding the grid to vehicle or vehicle to grid, to convert electric vehicles batteries as storage. Okay, so the owners of the electric vehicles have two options, as I said. He can absorb this energy and use it at low price, or can send it back to the grid when demand is high. So there is solutions, but it's important not to lose this energy. Okay?
Questions?
I have a question just about the formula that you showed, no?
You mean the model?
The formula.
The formula.
Of the capacity with curtailment.
Yeah.
About that. So the factor curtailment is negative or positive factor in there? Not this one, but the one updated with the additional factor, yeah?
Yeah, you mean this one?
Yeah, exactly. So I'm just to understand, just to clarify. So the curtailed energy in this formula is added, like an additive term, or is it negative?
No, it's a percent, okay? Because we divide the actual energy output. The actual means actually the power sent to the grid, okay, just, okay, over the maximum possible. The maximum is the maximum. The system can generate. So it's a percent. For example, in Jordan, the capacity factor using this equation is 36.1 for wind. Okay, but if we use the one I suggest, this will be more. The capacity factor will be more, which reflects the real performance assessment for wind. Okay.
Okay, so it is in percentage.
In percentage, yes. Because the maximum always bigger. Yeah.
Any other questions? Well, actually, I didn't get the point from vehicle to grid. If I have an electrical
Do you have
car,
it?
I do not do this. I mean, because battery time, durability of battery, when you make this cycle,
This is actually good.
that makes the shorter battery life, and I have to pay for any battery. I mean,
Do you mean the degradation
Yes.
of the battery?
I mean, if I fill my battery for my electrical car, I do not give this energy to the grid. because for every cycle of this, discharge and charge,
Yeah, this is
I
actually
lose my durability of my battery.
this is actually a good point, but in this case, you charge the battery use slowly, okay, slowly, because it takes around 7 hours to charge. The battery use is very safe, not the fast charging any. The fast charging make degradation or affect the battery electricity.
But every 5 cycle also makes this.
But when you charge it slowly, it won't impact the age of the battery. But again, you have two options. You can use this free energy, okay, at low price, or you can sell it to the operator or the company, power company operator. Again, when demand is high.
Well, personally, I don't.
It's just a
Any other questions or suggestions? Maybe? Okay, thank you very much. So this is your.
Thank you.
So maybe you can. Thank you. So we are very many. So we are also making broadcast of this given, as I brought you from the CNT submission system, so broadcasting. Now I think this is time